All right, everyone, welcome to Lesson 10. So previously on Lesson 9, we were introduced to the concept of the derivative, or the instantaneous rate of change of a function. Now what we're going to be studying today is how the derivative is itself a function. That may have been kind of how you thought of it last time, but last time we were kind of more focused on finding it at particular points. But this time we just are going to focus on finding the derivative kind of as a whole, or as just a function. So let us remind ourselves what the definition of the derivative is. So the derivative, commonly written as f prime of x, where we have the little tick mark there, is the limit as h goes to 0 of f of x plus h minus f of x over h. And remember, so this was called a difference quotient, and the derivative is the limit as h goes to 0 of a difference quotient. Now remember, there is another way of defining the derivative, and this is more useful for finding the derivative at a particular point. We can call it a. This is the limit as our x goes to a of f of x minus f of a over x minus a. Now this definition of the derivative is perfectly all well and good, but we're going to use this one more today, because this one's better at finding what type of function the derivative is. Notice that this is just the same function notation, only we have this tick mark here to differentiate it from f. All right, now in addition to seeing the derivative called f prime of x, you may also see it be called other things. So if y is f of x, then you may see f prime of x, like we have here. You may also see this as y prime. This is a common notation, especially for differential equations. You're going to see this a lot. And then here's another notation entirely. If you refer to this as y, we can call the derivative as dy over dx. And this notation kind of seems silly. Like, what are these d's? Why can't we just kind of cancel them out? Well, you can almost imagine this d as kind of like the triangle or delta that we saw last lesson. It's only that d represents a very tiny infinitesimal change in our y divided by the same type of change in x. And you may also see this as df dx if you choose to use f, or a final way is you may see this as d dx, and then in parentheses you put what you're taking the derivative of, which in this case is f. And these three right here, this is referred to as Leibniz notation. Leibniz is one of the inventors of calculus, and this is the notation that he introduced. And as we're going to see later, while this notation isn't really bad, in fact it's pretty easy to write with the tick mark, there's going to be some pretty useful things we're going to do with this sort of fraction interpretation of the derivative here. But it's good to be comfortable with all of these, because you'll see all of these different notations for the derivative from time to time. All right, now let's go ahead and compute the derivative as a function. So what I want to do for my first example is, if I have f of x as x cubed minus x, what I want to do is I want to find out what f prime of x is. All right, well, we did similar things last time. We're going to end up doing a bunch of algebra with this difference quotient here, but I want to do something a little bit extra this time. In addition to finding what the derivative is, I also want to graph these on the same graph and see if there's any kind of relationship between f and f prime. Now what I'm going to do first is I'm going to draw this. Now this is x cubed minus x. We may know what x cubed looks like. It's the polynomial, it kind of looks like this. But if we subtract x, things are going to look a little different. So how do we draw this? Well, let's factor it first. Maybe that'll make things better. I can pull out an x from both of these and make this be x times x squared minus 1. And then I can factor this further into x plus 1 times x minus 1. So this is another way of writing my polynomial here. And when we write it this way, when we write it in the fully factored way, we know when it's going to cross the x-axis, or when y is going to be 0. So if I draw my picture over here of f of x, it's a cubic polynomial with a positive coefficient here. So it's going to start from the negative area. Once we get to -1, it's going to hit 0. And it's going to go up a little bit, and then we know it needs to hit 0 at 0, so it needs to come back down. And then it's going to come through here, and then it needs to go through 0 one more time at 1, and then thereafter it's going to grow indefinitely. So this is a graph of f of x. All right, now what we're going to do is we're going to find out what f prime of x is, and then we're going to draw that, but in a different color to make it easier to see. So I'm going to find f prime of x. And remember, that's the limit as h goes to 0 of f of x plus h minus f of x over h. Okay, so if we substitute this in, kind of like we learned last class, I put x plus h into these. So I have x plus h cubed minus x plus h, and then I subtract the original function. So if I subtract this, this will be minus x cubed, and then subtracting a negative will make this plus x. And we divide that over h. Oh, I always forget to put my limits here. It's a bad habit. All right, now that I have this, I'm going to FOIL it all out. And that will help me see what's going to cancel, because that's always how this works. There's going to be a bunch of h's that appear that can cancel with this one. So if I cube this, now if you ever have some individual term cubed, there's a quick way of doing that. You do the first thing cubed, and then you have 3 times the first thing squared, and then times the second thing. Then you have another 3, and you flip which one has the square. And then finally, you just cube the last one. So this is a quick way of cubing something like this. Then we have minus x and minus h from this minus sign. And then we also have minus x cubed, and then plus x. All right, and then remember all of this is divided by h. Okay, now as usual with this, we're going to have some stuff canceling out. So we have x cubed canceling with this negative x cubed, and then we have negative x canceling out with this x right here. So that means that every remaining term, if we did this properly, should have an h left behind, and that is the case. Every one of these has at least h to the first power. So what we can do is divide by h. So this divided by h, we'll just get rid of that h, and we have 3x squared. We do this, we divide that by h, and we just have h to the first power. H cubed divided by h will be h squared. And then we have minus h, but then that divided by h will be minus 1. All right, so we've gotten rid of that pesky h in the denominator here, so now we're ready to evaluate the limit. So this does not have an h, this does not have an h, but these do, and as h goes to 0, each one of these will become 0. So what are we left with? We're left with 3x squared minus 1. And this polynomial, this function here, is going to be our f prime of x. All right, so now that we know what this is right here, let's go ahead and see if we can graph it. Now, this is a quadratic, right? And the coefficient for our x squared is positive, so this is going to be some upward-facing parabola right here. So if I were to draw this, let's see, so at x equals 0, I would go down to, say, -1. Maybe that's right here. And then I'm just going to go up like this. I guess it should be curved a little more, but I think you understand what I'm getting at here. There. That's what we want. All right, so here is our parabola drawn in red. Now let's see if there's a relationship between f prime of x and f of x. All right, well, let's see here. So remember, what does the derivative mean? The derivative is telling us about the rate of change of a particular function. So let's kind of follow from left to right and see how the blue function, or f of x, is changing. So as we start from down here, we move to the right, this is going up very quickly. So we're having a high rate of increase for this. And notice that at the same time, if we go to f prime at the same place, we're having a very high value for that. It's going to be somewhere up here. That means we're increasing quickly. But notice as we continue going along here, our rate of increase becomes slower and slower until finally when we reach this little plateau, we stop increasing. And that we have a corresponding behavior with f prime. We're still increasing, our rate of change is still positive until we get to this little hill, and then our rate of change is 0. We have a perfectly flat or horizontal tangent line right here, and the slope of this tangent line will be 0, meaning at roughly this one instant right here, we're not changing at all. Then when we go from here to here, we're decreasing, and at first we're only decreasing a little bit, and then our rate of decrease increases somewhat, and then our rate of decrease kind of slows again until it gets to 0. And then we have matching behavior of that with f prime. We start off a little negative, then we get moderately negative here, but then we get less and less negative until we get to f prime being 0 here, and we have another plateau. And finally, it seems after this point that we're just going to increase and increase more and more quickly as we go along this way. And to compensate for that, f prime will become more and more positive as we go along, representing that our rate of increase is positive, meaning we're gaining value on f of x. So f prime of x, the moral of this story here, is that f prime of x tells you whether your function is increasing, decreasing, or staying the same size. If f prime of x is greater than 0, then f of x is increasing. If f prime of x is negative, that means f of x is decreasing in that region. And if f prime of x is ever 0 somewhere, f of x is going to be flat, or it's going to have a little plateau, or the top of a hill, or the bottom of a valley, or something like that. So this is the relationship between the graph f prime and the graph of f of x right here. All right. So we got that one down. Let's take a look at another type of function and see if we can find its derivative. And then maybe we'll try to do the same thing. Let me flip back to blue here. Red was reserved for derivatives. So we have f of x. Let's pick a function that is familiar to us but can behave kind of strangely sometimes. And that's absolute value of x. So remember how this was defined. There are two different rules here. Absolute value of x is just x if x is greater than or equal to 0. But on the other hand, if x is negative, then we have negative x to compensate. Because remember, absolute value always makes things positive. So if we're negative, we need to put another negative there to make it positive. All right. So let's go ahead and graph this. So we have f of x equals x for x being positive. So that's just a diagonal line going up this way. And then we have negative x on the left side of our graph. And negative x looks like this. And they happen to meet at 0, because if I put 0 in for this, it's 0. And if I look at the limit as x goes to 0 for this, I get 0. So they kind of meet right here. So this is f of x. All right, now let's see if we can get f prime of x. So kind of like how f of x was a piecewise function, it turns out that f prime of x will also be piecewise. Now let's first consider the case where x is greater than 0. And we'll talk about equal to 0 in a little bit. All right, so if x is greater than 0, then we use this function, right? So f prime of x will be the limit as h goes to 0 of f of x plus h minus f of x over h. All right, so, but f of x in this case is just x. So we could just put x plus h here with the limit. And then we subtract f of x, which is x, and we divide by h. All right, well, these will cancel. And then we have h over h. That's just going to be 1. So it seems like for f prime, x greater than 0, that's just going to be 1. And it makes sense because the slope of the tangent line to this is, like the tangent line for this function is this function because it's a straight line. And the rate of increase is a constant 1. For every unit we go to the right, we're going up 1 unit as well. So that's going to be this. And in the same way, if x is less than 0, then if we do similar work here, and I'll leave that to you, we're going to see that f prime of x will be negative 1. And that also makes sense because we're continuously decreasing at a rate of 1 unit going this way. So if we were to draw f prime of x so far, we would have negative 1 all on this side, and then positive 1 on this side. All right, but the problem is what's going to happen at 0. So we have this little kind of sharp edge right here at 0. So let's see what happens at 0. So let's try to figure out what f prime of 0 is. Now for this, I'm going to use the definition of the derivative at a particular point right here. So I'm going to have the limit as x goes to 0 of f of x minus f of a, or 0, over x minus 0. All right, well, we could definitely simplify this right away. We have f of x minus f of 0. But if we plug 0 into the absolute value, that's just going to be 0. And on the bottom, x minus 0 is x. Okay, now, so we have this situation, but what is f of x? Now, on one side, it's going to be x, and on the other side, it's going to be negative x. So this is one where we need to kind of split it into two different scenarios here. If we look at the limit as x goes to 0 from the right, meaning we have little positive numbers, we're going to be using this definition. So it's just going to be x over x, which will be 1. And that makes sense because if we're on the right side of this at all, even for tiny little numbers, our f prime is 1. On the other hand, if we look at the limit as x goes to 0 from the left, we're having negative numbers, so we're going to have negative x. And this is negative 1. And that also makes sense because if we're negative at all, we're going to be on this line right here at negative 1. Okay, now let's remember our facts about limits. If we want the two-sided limit to exist, the limit is just x goes to 0 in general, then both the left and the right limits need to agree. But what's happening here is that these limits don't agree, which means that this limit does not exist. So what is this saying? This is saying that f doesn't have a derivative at 0, because if you try to figure out what the derivative is, you get a nonsensical limit. So if we were to try to put open or closed holes here, we would have two open holes here and then no filled in one because we don't have an f prime of 0. So even though this function f of x was continuous and defined for any real number you want, including 0, it turns out that f prime was not defined for all x. So f prime of x exists as long as x is not 0. But if x is 0, then we don't have a derivative here. And intuitively speaking, the function can't decide whether it wants to agree with this side, saying it's decreasing at a rate of 1, or agree with this side, saying it's increasing at a rate of 1. It doesn't know which one to pick or anything in between, so it doesn't return anything at all. So this is our first example of a function that is said to be not differentiable at a point, meaning that there's a place where this limit doesn't exist. So let me talk about what that means in more detail. All right, let's define what differentiable means. So a function f of x is differentiable at a point x equals a if f prime of a, so the limit as x goes to a of f of x minus f of a over x minus a. Alternatively, we could write this as the limit as h goes to 0 of f of a plus h minus f of a over h. Remember, these are the two different limit definitions. But we're going to be differentiable at a point if one or both of them, or it'll be both, if both of these limits exist right here. So if we find a situation where the limit doesn't exist, then we don't have a derivative there. And what that means is we can't meaningfully, or at least mathematically, very easily talk about the rate of change that's going on at that particular point if we don't have a derivative there. Now, so this is the technical definition. We need this limit to exist. But in future lessons, we're going to kind of shy away from using the limit definition of the derivative. So if we're not using the limits, how can I tell if something's differentiable or not? The easiest way to tell is by noticing places where non-differentiability can happen. And in general, there are three different situations where we're not going to be differentiable. Three non-differentiable situations. So the first situation is what we found in the last example. Let's say we have something that kind of looks like the absolute value function right here. If you have a sharp edge or a kink, then you're not going to be differentiable at this point. So you're not going to be differentiable right there if you have a sharp edge, right, like that, where it abruptly changes to being a different type of function altogether. The second type of situation where we also will get a limit that doesn't exist will be if your function isn't continuous. So if we have maybe a function going in like this, and then it just jumps to being right here, for example, then we're not going to have a derivative there as well. So if we have a discontinuous function or a place where we're not continuous, the graph isn't even connected, there's no way we're going to be differentiable. Now the third and final way is if we have something like this. Let's say we have a function that's kind of coming in like this, and then it's decreasing, and then it goes completely vertical. Like this tangent line, if I were to draw it in this place, would be completely up or down. So right here in the middle. And functions that look like this, you can imagine this is a graph of negative cube root of x, for example. This is not going to be differentiable there. Reason being is that your limit's going to end up going to infinity, meaning it won't exist. So we also need to watch out for vertical tangent lines. In this case, your derivative will not exist, but it's a bit different from these. These will not exist because the left and right won't match up. This will not exist because our limit will head to infinity here. So these are the three different types of non-differentiable situations. Other than these, most of the time if you see some kind of generic graph that looks smooth like this, then you're going to have a derivative everywhere there, unless specified otherwise. So these are the main cases we need to watch out for not being differentiable. Okay, one final fact, and this was kind of implicitly said here, if you are differentiable, then that also means that you're going to be continuous as well. So if you know that you can have a derivative, you're guaranteed to be continuous. On the other hand, just because you're continuous does not mean that you're differentiable. And the primary example of that are these absolute value functions. Because if we look here, this is continuous. I could draw this without picking up my pen at all, but I'm not going to have a derivative at this point here. So just because you're continuous does not mean you're differentiable. However, if you are differentiable, that automatically means you're continuous. Because if you weren't, you would have been violating this rule right here. So differentiable implies continuous, but continuous does not imply differentiable. And for that reason, we kind of consider differentiability a stronger condition than continuity. It's easier for a function, so let me summarize this. It's easier for a function to be continuous than differentiable. All right, so that's what I was trying to say right there. All right, I'm going to do two more examples here, and then that'll be it. All right, so let's take a look at another piecewise function, but this one won't be an absolute value. So let's say we have the square root of x for x greater than or equal to 0 and less than 1. And then we have x squared for x greater than 1. And we want to find f prime of x and the domain of f prime of x. Because remember, the derivative is a function, and it's defined anywhere the original function was differentiable. Okay, so let's first deal with this half right here. So let's see here. So let's take a look at this. We want to find f prime of x here. Then what we're going to do is we're going to look at the limit as h goes to 0 of the square root of x plus h, this is our f of x plus h, minus f of x, which is root x, over h. Now, similar to the examples we've seen before, if we have square roots in a limit like this, we're going to multiply by the conjugate. So I'm going to multiply the top and bottom by root x plus h plus root x, and then I'm going to do the same down here. All right, so when we do that, what do we get? Well, as always when multiplying by the conjugate, you're going to get what's inside here minus what's inside here. And then on the bottom, we're going to get something a little bit messy. Okay, now what happens is these x's cancel here, and then all we have left on top is an h, so the h's cancel right here. And then finally, what's going to happen is we're going to send h to 0, and we have just a 1 up here because everything canceled out. And then down here, we send h to 0, and we have root x plus root x is 2, or 1 over 2 root x. So this is our function here. Now, one thing to notice is that this is not defined for x equals 0 right here. And in fact, if we do the other form of the derivative right here, we'll actually get a limit that doesn't exist for x equals 0. Kind of like how we can't plug 0 into here. So when we're writing our f prime of x, and we make it piecewise, we're going to have 1 over 2 root x, but this will only be from 0 to 1, not including 0, because we can't plug 0 into this right here. And what's going on is this third definition, right, or this third type of discontinuity right here, we would have a vertical tangent line here because our derivative would go off to infinity. All right, now we already saw how to differentiate x squared from last class. Let me just remind you what happens. The derivative of x squared ends up being 2 times x. So if you want to see how to do that, I recommend taking a look at the previous video. So we have 2x, and we know this is going to work for x greater than 1. Now there's no place where this is undefined or anything bad happens, so we don't need to worry about restricting this domain at all. All right, now that was for x greater than 1. Oh, whoops, I forgot I was going to put this right here. I was going to put greater than or equal to 1 right here. So we would actually include 1 in our domain here. Now what's going to happen for f prime of 1? Well, on the one hand, if we approach 1 from the right, or sorry, 1 from the left. So if we're trying to figure out f prime of 1, see what that is. On the one hand, we have 1 over 2 root x, which is x goes to 1 from the left. That will end up giving us 1/2. But on the other hand, if we have 2x, and then x approaches 1 from the right, because these are all bigger than 1, it looks like that f prime's heading to 2. But kind of like the example with the absolute value, these are not the same, so f prime of 1 does not exist. All right, with all this in mind, let's go ahead and try to draw the graph of this. So let me get another piece of paper. Okay. So remember, f of x was root x for 0 to 1, and then x squared from 1 onwards. So if we were to draw root x, that's going to look like this. So this is at x equals 1. And then when we get there at 1, x squared is a parabola, right? And it looks sort of like this up to here, and then it turns on at 1, and it goes up like that. So what happens, and it's kind of hard to see this, let me kind of draw a picture to zoom in here. What happens is that this root x is kind of leveling off here, but then x squared goes up sharply here. So what happens is it's not as sharp as the absolute value one, but we do have a kink right there. And that's because f prime coming from the left wants to be a shallower 1/2, but f prime on the right wants to be a steeper 2 over there. All right, now let's draw a graph of f prime of x. So as x goes to 0, this is going to get really huge. This is going to go off to infinity. So actually, we have a vertical asymptote here at 0. And that's because right here, this is perfectly vertical, meaning we have an infinite rate of change. Now as we go to the left here, this is going to head to 1/2. And then we have a hole there. And then what's going to happen after that is we're going to go to 2. As x is bigger than 1, we start at 2, because we plug x equals 1 in here. And then we increase like 2x. But once again, none of these holes are filled in, and there's no hole, or there's no little point in between, because the derivative did not exist at this point, because there's a little kink there. All right, I want to do one final example where this time I'm not going to give us a function formula at all. I'm just going to draw a picture, and I want to see if we can draw f prime of x based on the picture of the original function. All right, so here's our last example. All right, so let me draw f of x. So f of x will come up like this, and then flatten out here, and then up here, we'll fill in that point, and then go down to a vertical asymptote, come up the other side, flatten, and then increase sharply, and then level off. All right, so this is our f of x. So this is a rather crazy function right here. It'd be probably kind of hard to write a formula for this. We'd have to definitely make it a piecewise function. All right, so this is f of x. So let's see if on the same graph we can draw f prime of x. Now remember, if our function's increasing, f prime will be positive, and the faster it's increasing, the more positive it'll be. And then the same goes for decreasing, only we're going to be negative. And the faster it's decreasing, the more negative it's going to be. And then finally, if we're ever flat or not increasing or decreasing somewhere, our derivative will be 0. All right, now let's see here. So as we start from here and go to the right, we're definitely increasing very fast. So we're increasing very fast. We're going to have a very high positive derivative here. But then it looks like we're starting to level off, and then we're flat right here. So we're going to start off very positive, but we're going to keep going down because our rate of increase is decreasing. And then we're going to hit 0 at the same time that we have that flat part right there. Then what happens is we're actually going to begin decreasing, and then we're going to decrease really fast right here. So we're going to go negative, and then we're going to go very negative. But then we stop decreasing as fast, so we're kind of leveling off here. And then it looks like right as we slide into x equals 0, we're going to be flat again. So we're coming up here to 0, but then we see that we have this jump right here. And remember, that was one of the places where we can't have a derivative. So I'm going to put a little circle in there, meaning that there's no derivative there. And then we're going to start following this one. So let me reiterate this again. So we start from the flat point where our derivative is 0. We're increasing very negatively and then only a little negatively here, and then we flatten out to 0. So we have very negative and then less negative and then 0. All right, now for this next leg of this, we're going to start with f prime being 0 because this also looks flat, and then we're going to decrease more and more and more and more as we go towards this asymptote. So we're going to start here, and then we're going to decrease more and more and more as we go this way. So kind of like how the function itself has an asymptote, we're also going towards the same asymptote right here. Now on the other side of the asymptote, we're going to be increasing at the same speed that we were decreasing over here. So since we're increasing, and we're increasing very fast close to the asymptote, our f prime is going to be way up here. And it's going to be very positive until we get to this little flat area here, in which case it will be 0, around close to this flat area. And then very quickly, it looks like we're going to go from being flat to increasing a little bit to increasing, and then we have a vertical tangent line. So we're going to increase very sharply, and then we have an asymptote with our derivative, because this is going to go off to positive infinity as we get to this point. So I'm going to draw like a red asymptote here, because once we get to here, our derivative goes to infinity. Then once we kind of come on the other side, we're still increasing really fast because we're coming off of the infinite increase, but then we're increasing more and more slowly over time, and it seems like our rate of change is heading towards 0. So we start off, we're increasing super fast again because we're still close to this, but then we're going to level off towards 0 as we go this way. So this is our graph of f prime of x. Now, if this seemed a little bit confusing at first, I would definitely recommend watching this part of the video again and making sure you understand this, because this is a really good exercise for intuitively understanding how the derivative as a function works. All right, that's it for this time, so I will see you guys in the next video.